Hello and welcome to another episode of Risky Business. Uh, Last time we took a look at the read CSR Hart ID and learned everything about that. So today we're looking at this next line, which is doing some computation of an address related to the PLIC. So we're going to be learning about the PLIC today. So first of all, off stream earlier, I was taking a look at the documents that SCIFI has, and here's an interesting one. It's schematics of the Hi-5 board. So not the actual chips, but the board itself. And so you can see they have schematics here that you can take a look at if you're interested in that sort of thing. So this is power supply, Freedom E310, USB to UART, and JTAG. So that's just a neat little one. I'm not well versed in electrical circuits, so I don't know too much about that, but I thought that was interesting to point out that they have that there. And so I think last time we were taking a look at this manual a little bit. They have two other manuals. They have a platform reference manual, and it looks like this has a lot of interesting stuff in it. So if you just look at the table of contents here, you can see there's all kinds of interesting stuff here. So like here's information about the UART. We'll probably be looking at that at some point. And then there's this other one too. So this is the E3 Coreplex series manual. And I'm not really sure the difference between the E3 Coreplex and the E300 platform. I guess the E300 platform is like a more specific of the high-level E3 Coreplex series, and then the FE310G000 is an actual chip, the one that's on our Hi-5 So I think this is like the highest level, and then this is like, you know, the most specific. That's my interpretation anyway. I could be wrong about that, but so looking over this one, there is some stuff about the PLIC that I see. There's Introduction 1.4, and there's Chapter 5 in here that has information about the PLIC. And then if we look at the risc-v specs, this is the privileged level spec. And Chapter 7 has platform level interrupt controller. So that's what PLIC stands for, apparently. And I think this would be the place to start. So we're going to start by reading a little bit about this. So this chapter describes the general architecture for the risc-v platform level interrupt controller, which prioritizes and distributes global interrupts in a risc-v system. So PLIC overview. So the PLIC connects global interrupt sources, which are usually I/O devices, to interrupt targets, which are usually Hart contexts. The PLIC contains multiple interrupt gateways, one per interrupt source, together with a PLIC core that performs interrupt prioritization and routing. Global interrupts are sent from their source to an interrupt gateway that processes the interrupt signal from each source and sends a single interrupt request to the PLIC core, which latches these in the core interrupt pending bits. Each interrupt source is assigned a separate priority. The PLIC core contains a matrix of interrupt enable bits to select the interrupts that are enabled for each target. The PLIC core forwards an interrupt notification to one or more targets if the target have any pending interrupts enabled, and the priority of the pending interrupts exceeds a per target threshold. When the target takes the external interrupt, it sends an interrupt claim request to retrieve the identifier of the highest priority global interrupt source pending for the target from the PLIC core, which then clears the corresponding interrupt source pending bit. After the target has serviced the interrupt, it sends the associated interrupt gateway an interrupt completion message, and the interrupt gateway can now forward another interrupt request for the same source to the PLIC. The rest of this chapter describes each of these components in detail, though many details are necessarily platform specific, and those platform specific details would be the stuff in this manual here. So that was a very dense paragraph. I think we'll need to see this in practice to really get a grasp on everything it's describing in detail here. But from what I understand, it's kind of a sort of a message passing type of thing where there's these interrupt gateways, and so it sends like an interrupt notification, and then when you do the interrupt, then it sends an interrupt completion message on the interrupt gateway. So I've got kind of like a vague understanding of what you're talking about here, but I think this will become clearer as we study more. So let's move on. Interrupt sources. So RISC-V Harts can have both local and global interrupt sources. This HART term is something they use a lot that I'm not familiar with, but we know from the Hart ID that it was referring to a hardware thread. So I think that's what Hart means, but that is a foreign term to me. But anyway, RISC-V Harts can have both. I also don't know if Hart is a proper pronunciation of that, I should say, but for now I'm going to assume so, and let's continue reading. RISC-V Harts can have both local and global interrupt sources. Only global interrupt sources are handled by the PLIC. Okay. So when we're talking about the PLIC, we're only talking about the global interrupts, but there can also be local interrupts. So I guess that's good to know. So here we have a nice, pretty diagram of some actual circuitry. So what is this showing us? So gateway, interrupt request, IP priority. And then it flows through some circuitry. Interrupt notification, interrupt ID. So platform level interrupt controller conceptual block diagram. The figure shows the first two of potentially many interrupt sources, and the first two of potentially many interrupt targets. The figure is just intended to show the logic of the PLIC's operation, not to represent a realistic implementation strategy. Okay. And like I say, circuit diagrams I don't spend a lot of time looking at, so this is a little foreign to me. But I think that D shape is an AND gate, if I'm remembering correctly. And some of these have little crosses through the lines. I'm wondering if that means not. But anyway, I don't think we really need to study the logic of how these signals are produced. So let's move on. Local interrupt sources. Each Hart has a number of local interrupt sources that do not pass through the PLIC. Okay, yeah, so this is the stuff we were talking about that isn't related to the PLIC, the local interrupts. So this includes standard software interrupts and timer interrupts for each privilege level. Local interrupts can be serviced quickly since there will be minimal latency between the source and the servicing Hart. No arbitration is required to determine which Hart will service the request, and the servicing Hart can quickly determine the interrupt source using the mcause register. Okay. So that gives us some useful information. The mcause register can be used to determine the source of an interrupt. I don't know if that applies to global interrupts as well, but at least for local interrupts, that's something we can do. And local interrupts are things like software interrupts and timer interrupts for the various privilege levels. All local interrupts follow a level-based model where an interrupt is pending if the corresponding bit in MIP is set. The interrupt handler must clear the hardware condition that is causing the MIP bit to be set to avoid retaking the interrupt after re-enabling interrupts on exit from the interrupt handler. Additional non-standard local interrupt sources can be made visible to machine mode by adding them to the high bits of the MIP/MIE registers, with corresponding additional cause values returned in the mcause register. Okay. These additional non-standard local interrupts may also be made visible in the lower privilege levels using the corresponding bits in the MID-ELEG register. The priority of non-standard local interrupts relative to external timer and software interrupts is platform specific. So there are a number of registers relating to local interrupt sources, and it looks like they all start with an M is the convention there. So there's like mcause, MIP, MIE, MI-deleg. So I guess that's good to be aware of. I don't think that really matters to us right now, but that's good to know, I think. This is all gonna kind of like seep in, you know? That's kind of how learning goes, I find, is you immerse yourself in a topic and there's a lot of stuff and it's like, okay, I'm taking in words, but I'm not really, you know, understanding everything that's being said. It's like you're throwing all this information at me. But then when you go back to it later on, it's like, oh yeah, I remember hearing something about that, you know, and then you go and see it and it's like, okay, yeah, that all makes sense. So that's kind of the stage we're at right now, where we're a sponge seeping in information. So global interrupt sources. Global interrupt sources are those that are prioritized and distributed by the PLIC. Depending on the platform-specific PLIC implementation, any global interrupt source could be routed to any hard context. Global interrupt sources can take many forms, including level-triggered, edge-triggered, and message-signaled. Some sources might queue up a number of internet interrupt requests. All global interrupt sources are converted to a common interrupt request format in the PLIC. So level triggered, edge triggered, and message signaled. Level triggered and edge triggered, I remember from like circuitry. It's like where, like when it's the signal happens. Like I don't know a good way to describe it. Anyway, let's move on. Okay, interrupt targets and hard contexts. Interrupt targets are usually hard contexts, where a hard context is given privilege mode on a given Hart. Although there are other possible interrupt targets, such as DMA engines, not all hard contexts need to be interrupt targets. In particular, if a processor core does not support delegating external interrupts to lower privilege modes, then the lower privilege hard contexts will not be interrupt targets. Interrupt notifications generated by the PLIC appear in the MEIP, HEIP, SCIFI, UEIP. Okay, so I see the convention here. M is machine, H is hypervisor, S is supervisor, U is user. That's the naming convention. So MEIP, EEIP, SEIP, UEIP, bits of the MIP, HIP, SIP, UIP registers for MH, SU modes respectively. The notifications only appear in lower privilege does that say RIP? I can't. Let me take a closer look here. Where was that? XIP. That's wasn't very clear on my monitor. So on lower privilege XIP registers, if external interrupts have been delegated to the lower privilege modes, each processor core must define a policy on how simultaneous active interrupts are taken by multiple hard contexts in the core. For the simple case of a single stack of hard contexts, one for each supported privilege mode, interrupts for higher privileged contexts can preempt execution of interrupt handlers for lower privileged contexts. A multi-threaded processor core could run multiple independent interrupt handlers on different hard contexts at the same time. A processor core could also provide hard contexts that are only used for interrupt handling to reduce interrupt service latency, and these might preempt interrupt handlers for other Harts on the same core. So that was everything about interrupt targets and hard contexts, I guess. Now we move on to interrupt gateways. Then we have interrupt identifiers, interrupt priorities, interrupt enables, interrupt priority thresholds, interrupt notifications, Interrupt claims. Jeez, this is a long chapter. We might not read all this. We might skip around. Interrupt completion, interrupt flow, PLIC core specification, controlling access to the PLIC. So let's read some of this going bottom up. I want to read controlling access to the PLIC, PLIC core spec, and maybe we'll look over some of this other stuff. Because this is a ton of information here. So controlling access to the PLIC. In the expected use case, only machine mode accesses the source priority, source pending, and target interrupt enables to configure the interrupt subsystem. Lower privilege modes access these features via ABI, SBI, or HBI calls. The interrupt enablers act as a protection mechanism where a target can only signal completion to an interrupt gateway that is currently enabled for that target. Interrupt handlers that run with lower than machine mode privilege need only be able to perform a claim read and a completion write and set their target threshold value. The memory map for these registers should allow machine mode to protect different targets from each other's accesses using either physical memory protection or virtual memory page protections. PLIC core specification. The operation of the PLIC core can be specified as a non-deterministic finite state machine with input and output message queues with the following atomic actions. Write register, a message containing a register write request is dequeued. One of the internal registers is written, where an internal register can be a priority, an interrupt enable, or a threshold. Accept request. If the IP bit corresponding to the interrupt source is clear, a message containing an interrupt request from a gateway is dequeued and the IP bit is set. Process claim. An interrupt claim message is dequeued, a claim response message is enqueued to the requester with the ID of the highest priority active interrupt for that target, and the IP bit corresponding to the interrupt source is cleared. The value in the EIP bit is determined as a combinational function of the PLIC core state. Interrupt notifications are sent via an autonomous process that ensures the EIP value is eventually reflected at the target. Note that the operation of the interrupt gateways is decoupled from the PLIC core. A gateway can handle parsing the interrupt signals and processing interrupt completion messages concurrently with other operations in the PLIC core. So figure 7.1 is a high-level conceptual view of the PLIC design. So that's the diagram that we saw earlier that showed like the logic. The PLIC core can be implemented in many ways, providing its behavior can always be understood as following from some sequential ordering of these atomic actions. In particular, the PLIC might process multiple actions in a single clock cycle, or might process each action over many clock cycles. Okay, so we have taken in quite a lot of information already today. It has been quite a lot of reading. So here's interrupt flow. I do want to look at this diagram and see what the interrupt flow is like. So figure 7.2 shows the messages flowing between agents when handling interrupts via the PLIC. So you have an interrupt source, which signals an interrupt. That goes to the gateway, the interrupt gateway, which sends an interrupt request to the PLIC core. So the PLIC core then sends an interrupt notification to the target. So then the interrupt handler runs, sends an interrupt claim to the PLIC car. The PLIC car sends a claim response back. And then once the handler is done, it sends an interrupt completion to the gateway, and then the gateway sends the next request. So that is the flow of all this. So that's kind of a complicated thing. But it's certainly understandable what's happening here. Like I said, it's just a flow of messages passing between these different stages, right? So at the very far end here, we have the interrupt source, which is like I/O devices, and then all the way on the other end, you have the target, which is you know, the thread that actually runs the interrupt handler. And then the stuff in the middle is a gateway and a PLIC core. And so the gateway handles queuing up the request, basically. So it sends out an interrupt request, and then when it's done, the handler sends the interrupt completion to the gateway, and then the gateway sends the next request. So that's kind of like your queue, right, so to speak. And then, so like the interrupt source generates all these signals, it gets queued up, and then the gateway handles sending them after each one is completed. And then the PLIC core does this little dance between the core and the target with notifications and claims and claim responses. So that's the high-level overview of what all this interrupt nonsense is. So what does it say below this? The gateway will only forward a single interrupt request at a time to the PLIC and not forward subsequent interrupt requests until an interrupt completion is received. So that's what I was saying. It's like a queue. The PLIC will set the IP bit once it accepts an interrupt request from the gateway, and sometime later forward an interrupt notification to the target. The target might take a while to respond to the new interrupt arriving, but will then send an interrupt claim request to the PLIC core to obtain the interrupt ID. The PLIC core will automatically return the ID and clear the corresponding IP bit, after which no other target can claim the same interrupt request. Once the handler has processed the interrupt, it sends an interrupt completion message to the gateway to allow a new interrupt request. So that tells us more about what this dance is that's happening between the PLIC core and the target. So the idea here is that you know, you've got this gateway queue, it sends an interrupt request to the PLIC core, and then the PLIC core sends a notification to the target because the target might take some time to say, okay, I'm gonna handle this interrupt now. And then once the target thread says, okay, I'm gonna work on this interrupt, it sends back an interrupt claim to the PLIC core. And when it does the interrupt claim, the PLIC core, let's see where it says that. Okay, so when the PLIC core accepts the interrupt request from the gateway, it sets a bit in some register, the IP bit. And then some time passes, some unknown amount of time passes, and then it forwards the interrupt to the target, and then that's the interrupt notification part. And then when the interrupt claim happens, so now after some amount of time, the thread says, okay, I'm gonna work on this interrupt. It sends the interrupt claim to the PLIC core. And what happens then? So we're at the PLIC core. We've received the claim request, and so it looks like the PLIC core sends the thread an interrupt ID. And then it clears the IP bit. And then after that, no target can claim the same interrupt request. So you can think of it like a mutex, sort of, right? So you're saying this is locking on the interrupt, so no one else can access it. No one else can do that interrupt because someone has claimed it, right? They've claimed a lock on it. So that's basically what's happening there. And then the handler processes the interrupt, and after it's done, it sends the completion message to the gateway. So I feel like I understand now the total overview of what the PLIC is doing, how all of these pieces fit together. So I think now is a moment to go to the whiteboard and write out what we've learned. First of all, I remember looking it over yesterday. I made a little typo in my notes. So this is supposed to be CSRRS. So I'm going to correct my notes. And also, this, I believe, is technically a register, a general purpose register. So like we had that variable, right? That temp variable with the CSR stuff that we were looking at yesterday in the inline assembly. We created a temp variable in C, and then we did some inline assembly that referenced that variable to get a value from the machine instruction into that variable. But technically, I believe what that variable boils down to in assembly is it's actually put in a general purpose register. And then this instruction is referring to an actual register. So that's my understanding of this. But now we're moving on to what we learned today. And we're not done for today. We're going to learn more. But I want to take a note of what we've learned so far. So we've learned about the whole PLIC business. So PLIC. First of all, it stands for platform level interrupt controller, something like that. Platform interrupt controller, I think. So let's scroll up here and see. Yes, platform level interrupt controller is what PLIC stands for. All right. And so basically what happens is you have some magic IO device. Right, there's like a little gnome in your chip that runs around and sprinkles some fairy dust, and that sends out a interrupt request. So are they called interrupt requests? Let's look at the diagram again. I believe that's the terminology. interrupt signal. It sends an interrupt signal. So we're going to say interrupts signal, and this gets put into, you know, a big waiting queue. So there's a big line to the doctor's office, and we've got all these spots where all the signals go, right? So signal, signal, signal. Right, so there's a bunch of signals waiting to be processed. And so we've got this queue, and then there's this gateway, right? So we've got like Gandalf over here. Holding back all these things in the queue, and then he's like, okay, you can go. So one of the signals goes off in this, this is the gateway. And he's like, okay, you can go. And then, so that's the interrupt request that goes. So this is the interrupts request, and that goes to the PLIC core. And so the PLIC core, it sets some IP bits when it receives the request, and then it sends a an interrupt notification to the target. So let's see here. I'll draw it down here. So here's the target. So this is like a thread running on our chip, running on the Hi5 right? And the PLIC sends an interrupt notification to the target, and then the target is all like, yo, give me the ID, bro. I wanna claim that interrupt. So he's all, yo, give me that interrupt, bro. And claims the interrupt. And this is like, I'm going to say this part here is basically, this is pretty much like mutex holding a lock on a resource. So once that happens, the PLIC car sends back to the target the claim response. And this has the like, I guess it's the interrupt ID that has, that it's sending back to the thread. Yeah, so the PLIC car will automatically return the ID. Okay, so once all of that's done, the thread does its work, and then it sends the finished message, the interrupt completion, to the gateway, and the gateway sends the next request. So the target's like, yo, Gandalf, my wizard, I'm done, bro. And then Gandalf's like, okay, I'll send the next signal through. That right there is how the whole PLIC business works. Gremlins and all. So, with that understanding out of the way, we want to know more about, I think, interrupt enables, because the code here is disabling all interrupts. So that's what we're doing, is we're disabling interrupts. So we're clearing out some memory, and we're computing where to clear it with these magic values. So we want to know what it means to disable interrupts, how that's like done, and we want to take a look at the SCIFI documentation about PLIC, because that'll tell us, that should tell us the actual values, like where in memory you do this stuff, which is what the code is referring to. So let's take a look at interrupt enables, because I would assume enables would also be involved in disabling. That's my assumption. So let me see here. We're going to go 15 minutes over than the usual time we stopped today, because we started 15 minutes late. So we've still got some time here. Each target has a vector of interrupt enable bits, 1 per interrupt source. The target will not receive interrupts from sources that are disabled. The IE bits for a single target should be packed together as a bit vector in platform-specific memory-mapped control registers to support rapid context switching of the IE bits for a target. IE bits are WARL fields that can be hardwired to either 0 or 1. So a large number of potential IE bits might be hardwired to 0 in cases where some interrupt sources can only be routed to a subset of targets. A large number of bits might be wired to 1 for an embedded device with fixed interrupt routing. Interrupt priorities, thresholds, and Hart internal interrupt masking provide considerable flexibility in ignoring external interrupts, even if a global interrupt source is always enabled. Okay, so what we're saying here is you can clear these bits to 0, which presumably is what we're doing here, I'd guess, is we're talking about these IE bits on the target. I think that's what this is doing here, is it's clearing those to 0. And they could be hardwired. There could be ones that are hardwired to 0 or 1. So if it's 0, you're saying ignore it. And if it's 1, it's saying you're always going to handle it. But the footnote here says that there's considerable flexibility in ignoring external interrupts, even if a global interrupt source is always enabled. And specifically what they're referring to is the ability to set interrupt priorities, thresholds, and Hart internal interrupt masking. So those are the mechanisms by which you can ignore external interrupts, even if it's hardwired to always be enabled. But it looks like we're just doing a mem0 here, so we're clearing everything. And then we set all the priorities to 0, which is one of the mechanisms that it talked about for ignoring interrupts if it's hardwired to 1. And thresholds are another mechanism that it mentioned in the footnote. And we're setting the thresholds to 0 as well. So that all makes sense in terms of our mental model that we have now. The steps that we're doing here seem to make sense if you're wanting to ignore interrupts. These are the things that it's talking about in the documentation here. So there's also the chapter on interrupt priorities here, right above the one we just read, and there's the one below it which talks about the thresholds. So I suppose we should read those since we are messing with them, right? So all of this stuff we're doing is the PLIC init. So let's remember that. When we init the PLIC, what we're doing is turning off all the interrupts, and we also set some stuff in a structure. So we set up this PLIC structure, and then we just turn off the interrupts by setting these 3 things. So let's take a look at priorities, I guess. Interrupt priorities are small unsigned integers with a platform-specific maximum number of supported levels. The priority value 0 is reserved to mean never interrupt, and that's what we're setting. You can see right here, set all priorities to 0. That means never interrupt. And interrupt priority increases with increasing integer values. Each global interrupt source has an associated interrupt priority held in a platform-specific memory-mapped register. Different interrupt sources need not support the same set of priority values. A valid implementation can hardwire all input priority levels. Interrupt source priority registers should be WARL fields to allow software to determine the number and position of read-write bits in each priority specification, if any, to simplify discovery of supported priority values. Each priority register must support any combination of values in the bits that are variable within the register, i.e. if there are 2 variable bits in the register, all 4 combination of values in those bits must operate as valid priority levels. In the degenerate case, all priorities can be hardwired to the value 1, in which case input priorities are effectively determined by interrupt ID. The supported priority values can be determined by follows. write all zeros to the priority register, then read back the value. Any set bits are hardwired to 1. Okay, that makes sense. So do we read it out to see which ones are set, or do we just it looks like we're just clearing it to 0. We don't care about seeing which ones are hardwired. But if we wanted to see which ones are hardwired, we could read back the value, and if there are any set bits, that means they're hardwired to 1. So that's a cool little thing to note. So 3, write all ones to the register and read back the value. Any clear bits are hardwired to 0. Okay, so they're saying you can do the same thing to figure out which ones are hardwired to 0. Any set bits that were not found to be hardwired in step 2 are variable. The supported priority levels are the set of values obtained by substituting all combinations of 1s and 0s in the variable bits within the priority field. So now I imagine that SCIFI would document which ones are hardwired and which ones are variable in their implementation. But if they didn't document that, we could actually figure it out by doing this trick here that it's describing. So that's pretty cool. But like I say, we're just zeroing it all out. So there could be stuff that's hardwired to 1, but anything that's variable, we're setting to 0. Which means never interrupt. Now there's also interrupt thresholds that we want to read about. Each interrupt target has an associated priority threshold, held in a platform-specific memory mapped register. Only active interrupts that have a priority strictly greater than the threshold will cause an interrupt notification to be sent to the target. Different interrupt targets need not support the same set of priority threshold values. Interrupt target threshold registers should be WARL fields to allow software to determine the supported thresholds. A threshold register should always be able to hold the value 0, in which case no interrupts are masked. If implemented, the threshold register will usually also be able to hold the maximum priority level, in which case all interrupts are masked. So a simple valid implementation is to hardwire the threshold to 0, in which case it has no effect, and the individual enable bits will have to be saved and restored to attain the same effect. While the function of the threshold can be achieved by changing the interrupt enable bits, manipulating a single threshold value avoids the target having to consider the individual priority levels of each interrupt source, and saving and restoring on the interrupt enables. Changing the threshold quickly might be especially important for systems that move frequently between power states. So that's interesting that we're setting the threshold to 0 then. Because that means don't bother with thresholding. Whereas if we're really trying to disable interrupts via thresholding, you wouldn't set the threshold to 0. You'd set it as high as possible, right? But in this PLIC init, we are simply setting the threshold to 0. So fair enough, I suppose. So I guess that's everything we want to read about in this document. And we have 5 more minutes today. So let's start taking a look at what the SCIFI document has to say. So let's start with the introduction to the PLIC. The E31 Coreplex includes a risc-v standard platform-level interrupt controller that can be configured to support up to 32 inputs with up to 31 programmable priority levels. Okay. Let's see here. Platform-level interrupt controller, Chapter 5. So this chapter describes the operation of the PLIC on SCIFI systems. The SCIFI PLIC complies with the RISC-v spec and can support a maximum of 1023 external interrupt sources targeting up to 15,872 Hart contexts. So memory map. The memory map of the SCIFI PLIC control register is shown in table 5.1. So let's take a look at that right away. So here is the memory map for the PLIC. Now we are getting a value here. So we're doing base address plus PLIC priority offset. Or we were looking at this one, the PLIC enable offset. So I'd like to see where we call PLIC in it so I could see what we're passing as the base address. But let's see here. So these are the addresses. So there's reserved, source 1 priority, source 2 priority, all the way to source 1023 priority. So this is a read-only pending array, end of pending array, some reserved memory, target 0 enables, target 1 enables up to the highest value, then some reserved memory, and then we have priority threshold, claim complete for each, so a pair of threshold and claim complete for each target in this memory here. So I want to explore our code a little bit. Where is, so here's the demo GPIO, and I want to see where we call PLIC in it. So so we're passing in address of gPLIC, PLIC base address, PLIC num interrupts, PLIC num priorities. Now let's take a look at the signature again. So the first thing we're passing is this PLIC structure. Then we're passing the base address, the num sources, the num priorities. So when we're referring to the base address, we're talking about this PLIC base address. So now where is the PLIC base address defined? So it must be defined in here. Or no, that's just defined in here, isn't it? No, it's not defined in here. This has the enable offset, but it doesn't have the base address. I want to know where the base address is defined. I wonder, do we define that in the program itself? No. So we need to figure out where the PLIC base address is defined. It might be in platform.h. So I mean, it's got to be in platform.h, PLIC driver.h, or in coding.h. I'm surprised it's not in the in the PLIC.h. Okay, here we go. So it's in platform.h. PLIC base address is 0x0c000000. And if you look here, 0x0c000000. So this is the address specified as the start of the PLIC memory in this SCIFI documents, and you can see it being referenced here. So that points to a reserved memory, but then we're adding some stuff to it as well. Oh, and we're out of time. We're a few minutes over, actually. So we will have to continue this exploration tomorrow. So thank you everyone who watched today. And did I never update the chat? Sorry about that. There wasn't any chat anyway, though. But thank you everyone who watched, and thank you everyone who watches on the YouTube archive at risky.tv. And you can follow me at HMN_risky on Twitter to get updates about this series. And I will see you next time. Stay risky, everyone.